I took this doubling every year and extrapolated it 10 years from 1965 to 1975, from 60 components to 60,000 components on a chip.
First thing you have to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
Good afternoon, everyone. So not sure how many of you were here early enough to hear the song "You Need to Calm Down," which is the one that we played. I usually pick a song before each lecture, and sometimes, you know, like probably the most like exhausted process of preparing my lecture is try to select the right song. And the reason why I select that one is just because I feel like a lot of you are kind of like under like anxiety or stress because the midterm is coming up, right? But one thing I do want to tell you is that you just need to calm down because it's not that hard. And tomorrow we will have a lecture. And after the lecture, you are probably going to have a better idea about what's going on. And it will give you a very good overview of in all the high level bits that you should cover in the midterm, right? And probably another thing that I will ask you in the midterm is like list one song that I played before the lecture. Hopefully that will encourage you to come earlier. So so as our tradition, usually I really would like to set up the stage for the upcoming lectures. So that's why we have this recaps, and they are. And if you see that I have something that's in the recap slide, meaning that there are key concepts in computer architecture that you should never forget. And for pipeline processor, well, we expect it to run smoothly, but most of the time we can because we have three different types of a pipeline hazard. Structural hazard, meaning that we have resource conflicts or competitions that cannot allow simultaneous execution of instructions in a pipeline. The control hazard means that the PC cannot be can be changed by the instruction, so we don't know what's the next instruction to execute. The data hazard means that an instruction depends on the output of another instruction that is not yet generated or propagated when the instruction needs that. So if you look at the wording, right, when I needs that is not yet generated or propagated. So what does that mean is that you have data dependency, but as long as you can have the value ready before another instruction needs that, the data hazard doesn't exist. So previously, we learned about like data forwarding to address the data hazard. And we learned that we can use stalls to solve data hazard as well and structural hazard as well, but it's not as efficient as we would imagine. However, even with full data forwarding, another limitation is that if the data is not generated yet, so like this case, because the load word only generates its outcome at the end of memory stage, even though I have full forwarding, I still cannot forward that value from the execution stage to others because that value is just not ready. So here's the case why the added instruction must wait for one more cycle, or say must stall for one more cycles. So yesterday, I also received a lot of questions regarding like how to draw the pipeline diagram. And the answer is that if you go back to look at the tips that I gave in the 8th lecture of the class, which on the page 9, which I show up many times yesterday, you will figure out that because the edit instruction doesn't get its requested value of T0 ready, so it has to stall in the instruction decode stage for one more cycle. And for stall word instruction, because the next stage is instruction decode. However, because edit instruction is occupied in the instruction decode stage, so the stall word instruction cannot going forward. So that's why this part of the pipeline diagram looks like this. And again, because we want to avoid a structural hazard, so all the instruction must go through all 5 different pipeline stages, even though you will see like later on, you know that for the branch instruction, we don't even do anything for memory and write back, but we still have to go through all of them because of the guideline that I gave you guys in the 5-stage pipeline. So it doesn't matter what kind of processor are given. They should all follow that tips. They should all follow that guidelines in drawing the pipeline diagram. So if you memorize or say you are familiar with what I wrote on the slide, you don't have to like specifically ask, oh, what should I do with data forwarding? What should I do with branch prediction? Just look at that guideline, right? If you don't have that kind of information, just don't forward. If you are not ready to fetch, just don't fetch, right? So that's the thing I really want you to go back and look after you come done after finishing your assignment 1. So we talk about like, so we finished talking about data hazard in the last lecture, and then we start with the control hazard. And the reason why control hazard is important is that, well, so being honest to you, like in this instruction set architecture, we said there are 20% of branch instruction on average. But if you move it to x86, which is the architecture that you are using more often, the branch instruction is actually 33%. So if you look at the pipeline design right now, we have in a 5-stage pipeline. If you have the branch instruction and without any additional treat to address the control hazard, you have to stall for 2 cycles for every branch, meaning that whenever you have a branch instruction, you have to wait for 2 more cycles, or effectively the branch instruction will take 3 cycles to execute, meaning that your average CPI will be bring up 40% just because of this 20% of the branch instruction. So that's not good, right? So we said we can do statically not taken predictor because that's easy to do. You don't have to have a cheat sheet of a branch target. However, the accuracy is only 25%, and combining that 25%, it doesn't help that much in lowering your CPI. So we introduce a better approach, which is dynamic branch prediction. So the basic concept of dynamic branch prediction is like this. So first of all, because we have the difficulty of knowing the target address, but fortunately, if you look at the encoding of branch instruction is essentially an I-type instruction. By I-type, it means that its operand is simply an immediate, and the 2 register operands are just used for comparison, but not related to address calculation. What it means is that everything that the branch PC needs to calculate its target PC are constant. And because it's constant, no matter how many times you execute that branch instruction, the target PC, as long as it's the same instance, it's an instance from the same static instruction in the branch, then the target PC would never change. So once you have that branch instruction go through your pipeline once, if you can keep like stealing the result from your execution unit, your address calculation part of your circuit, then you can put that information into this stuff called branch target buffer. So what this would, and additionally, you maintain a set of states that help us to predict if it's going to be a taken or not taken. So what would happen is that with that help, when I have a branch instruction, if I found there is a match in the branch target buffer, I could immediately use that target PC as the input of my PC for the next cycle if the state tells us that you should predict taken. So so here is the operation of the very basic 2-bit bimodal local predictor. So in local so by local it means every branch instruction would have its own state and it's maintained locally, so it's not affected by the outcome of other branch instructions. So each state is just associated with the branch PC, and it's called 2-bit because we have 2-bit in maintaining the state. And it changed the state based on the actual outcome of your branch. And if we guess it right, like many of the prediction, is that if you guess it right, there's no penalty and you got the benefit of executing your instructions earlier. However, if you guess it wrong, you just need to clear the pipeline registers for mispredicted instructions and refetch the instruction that should be on the correct direction after the execution stage of your branch, which is essentially the same performance as without branch prediction. So the good thing about any kind of branch prediction is that at least you lose nothing, right? And how this bimodal predictor works is that, well, a lot of people will fool you with this very complex state transition diagram because they think as long as you can draw something like automata, you sound like a computer scientist. But the real truth behind this seems to be complex diagram is that it's just a saturate counter in a way that it increments whenever your branch outcome is taken. It decrements whenever your branch outcome is not taken, and it's saturated at 3, and the lower bound of the saturate counter is 0. And whenever the value is greater and equal than 2, then you predict taken. Otherwise, you predict not taken. So that's the idea of this bimodal predictor. And it's the simplest kind of branch prediction. And if you go through the code that we had here, you will figure out that for this branch predictor, it would reach 75% of the accuracy. But as I can imagine, a lot of you, if I said, well, you only get 75 in your midterm, I don't think any of you would be satisfied with that. So we definitely want our branch prediction to be better, right? So we want to do a better job. We are not satisfied with just 75. So how can we do a better job? That would be the first topic that I'm going to talk about today. So today I'm going to introduce the 2-bit, 2-level global predictor that has been once used in the Pentium processors developed by Intel. So for 2-bit local predictor, right? If you observe, so the big issue why this 2-bit local predictor is not performing well is because for the branch X, we can only achieve 50% of the accuracy. However, the only reason that we can achieve only 50% is because we only have the knowledge of what's going on here, and we only see an alternating pattern here, right? So it becomes really hard. So it's just taken, not taken, taken, not taken, right? So it becomes really hard that for the local predictor to make it right, because it's just bouncing around between 2 counter values, and most likely you can only do you can only get it right in 50% of the time. And it's even worse if you start it with a state like 1, 0 or 0, 1, and potentially you might be able to even get like 0% accuracy. So the 2-bit predictor doesn't work very well for this case. However, another thought you have is that if you look at the actual outcome of all the branches we have, you will figure out there is a clear pattern here. So if you look at that, right, followed by a not taken. Your branches, no matter it's X or Y, they will have 3 takens. And then followed by a not taken, you will get 3 takens, right? And that pattern repeats forever. So another idea of branch prediction is that if we see there's a pattern in your program and it shows up in a lot of in many different kinds of code. If we find that kind of behavior frequently occurs in our applications, can we use that kind of behavior to make a better prediction? So here comes the idea of global history predictor. So for this part, still the same. We still have a mux from with input from PC+4. We still have the branch target buffer. However, what you will find different is that now the branch target buffer doesn't contain states. We maintain the states separately, and the states are not associated with the branch PC anymore. In fact, it will associate with the history of all the branch results. So in this kind of branch predictor, we need to additionally maintain a global history register called GHR. So this global history register is simply a sequence of zeros and ones that records if the previous branch is taken or not taken. And usually we represent a not taken result as 0, a taken result as 1. And whenever a branch PC comes in, instead of using the branch PC to find the state, we now use the global history register value to match the history, the states. So when you see this global history register, it represents the value of 4. So meaning that whenever I have a branch, I still get a target PC from the branch target buffer. However, when I decide to predict taken or not taken, I use the global history register. And if it says the value currently is 4, I just go through the 4th entry in the table of states. And again, it's still a saturate counter. And if the state is greater or equal to 0, 2, we predict it's going to be taken. So for this case, because it's 2, so we predict the branch is taken. So that's the basic idea of global history register predictor. So if we use that concept in the code like this, then what would happen is that now when I equal to 0, for branch X, and let's say now the GHR is 0, 0, everything is 0, and we will definitely predict not taken, the actual outcome is taken. So one thing you will learn is that the next time, if you see GHR with 0, 0, 0, its state will be incremented by 1 as 0, 1. But let's keep going for now. When I equal to 0, when I meet, so this should be 1, by the way. So when I equal to 1, because I did I++ first, when I equal to 1, so previous branch is taken. So the GHR is now 0, 0, 1. And we haven't seen that GHR in the past. So suppose the state will be 0, 0. Predict not taken. The actual outcome will be taken. Now, I is incremented by 1. We go to branch X. And as you could imagine, the GHR is now 0, 1, 1 because the previous 2, they are taken. And we haven't seen that before. Predict not taken. The actual outcome is not taken because this time your I is 1. So when I equal to 2, let's go to, we go to branch X, and previous history tell you this is 110. So we have a 110 here, and the state is still 00 because we haven't seen 110 in the past. So we predict not taken, but the actual outcome is taken. So if we keep iterating, you'll feel, well, professor, it doesn't work so far. It's very bad. But one thing I want to say, you need to calm down, right? Let's keep going. So right now, when I equal to 3, branch is y. And if you look at the previous history, it's now 0, 1, 1. And you will see, hey, we have 0, 1, 1 here, right? And the last time is 0, 0, and it was not taken. So for 0, 1, 1, it's still 0, 0, because this is a saturated counter, so we predict not taken. And however, this time it's going to be a taken. So the next time you see this, it will be 0, 1. Okay, still not working, professor. I'm losing my patience. Okay, you need to calm down, right? Let's have a few more rounds. Let's give it more chances, right? So now, when I equal to 3, x should be an odd number, so it's going to be not taken. And at this time, we have three ones in the past, in a history, but we never see this in the past. So, well, even though this is not taken, we predict not taken, and it seems like we guessed it right, but it's just because we are lucky, right? So you start to like not trust in me now, right? But just have more patience, right? So now when I equal to 4, y now previously we have 1, 1, 0, and we have 1, 1, 0 here, right? And for this one, because the last time is taken, so now the state should be 0, 1, right? And we still predict not taken. The actual outcome is taken, but did you see some lights here? Because the actual outcome is taken. So what it means that the next time when we interface with 1, 1, 0, it will predict taken, right? So did you see some lights here? So let's keep going, right? So if I have a branch X now, right? The previous 3 history, as you can see here, is 1, 0, 1. And we have 1, 0, 1 here in the past, right? And the previous result was taken. So it also goes to 0, 1. We still predict wrong, but again, the next time when we see this, we are going to get it right, right? So now, when I equal to 5, y branch, we see the history as 0, 1, 1. We have 0, 1, 1 here, right? And previously it was 0, 1, and the actual outcome is taken. So now, this time it's 0, 1, and as you can see, the next time is going to be taken again, right? So now, let's go to 5. When I equal to 5, you know this time x is going to be a not taken. And if you look at the previous history, is 1, 1, 1, right? So for 1, 1, 1, still not taken, and we still predict not taken because previously it already says not taken. So this one is actually coming from the outcome of the previous training, right? So when I equal to 6 for branch x, right? Previous history is 1, 1, 0. So 1, 1, 0, we had it here, and we said this time its history is 1, 0, so it's predicting taken, right? And the actual outcome is taken. And now, if you go to another round, you will figure out the history is 1, 0, 1, and this time it's taken, right? So if you keep iterating, you will figure out that everything after that point, after this point, everything after this point will become perfect prediction. So you get about 100% accuracy after you well trained your GHR predictor, right? So it takes longer time to train, but it works out. Okay, Harris, question.
So the state of each branch, is that separate from the GHR?
It's separate from the GHR.
Okay, so that means that even if we use the 2-level global register, we're going to have to also assign a state.
You will have states trained for each GHR value.
Okay, thank you.
Okay. Okay, so that's the basic idea of GHR. So, okay, David.
So I had a question about so this one is like the GHR is like 3 bits, but there's like more than like 4 different branches, and is that enough to like to make like accurate prediction?
So that's a good question. So if you have more branches, it may not be sufficient enough to accommodate, right? So usually, okay, so this is just a very simple idea, right? And usually, like in modern processor, the GHR is probably going to be like 10-bit. But you definitely don't want me to iterate over that kind of examples in a class, right?
I see.
Yeah, so that's why I made it short, right? So in fact, but that's a great question, and in fact, in places like the new, I would say like the latest Ryzen processor, they use I would say LTH branch predictor, which is a combination of predictors based on different lengths of history. The shortest is probably like 4-bit, but the longest could be like tens of bits. All right.
I see. Thank you.
All right. All right. So, well, so looks like this predictor already give you some confidence and some interest, and some of you are starting to thinking about, oh, what's the limitation, right? So why don't we just try this question for you guys to think, what's the limitation of branch predictor, and what's the pros and cons of each predictor for 90 seconds? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so well, so looks like we have a lot of you have some thoughts already, but sometimes the answer just looks like branch prediction. So what I would do is that I just send out the screenshot of the question, and I really like you to discuss with your friends, and hopefully that will change your mind and to lead us into like a very interesting discussion. So go ahead and start the group discussion. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so according to what you guys think, well, it looks like most of you think two of them would in favor global history predictor instead of the local predictor. So I do want to invite some of you to let me know what your group thinks, not you, your group. Okay, so I have our hero, Dui. What do you think?
So my groupmate said that it's 2 because for the ones with like the one with mod 10, because it doesn't fluctuate as much, it might be the case that the local predictor will do better. And then the same for the second one, it's just one branch. And with the local predictor, like I think we'll get like almost all of it correct. And we talked about how like in 3 and 4, there's more branches, and because it fluctuates more often, that the global predictor will do better there. So that's why.
Oh, so say
chose
that again.
2.
For the first one, which one is working better?
The local predictor, because it's a mod 10.
It's a mod 10, but why the local predictor would do a better job?
Because it doesn't fluctuate as often for the X branch.
Often.
Yeah.
But okay, but how about, but what does that mean is that most of the time, right? Most of the time you are going to see a single outcome from this branch.
Mm-hmm.
Is that right?
Mm-hmm.
And for this branch, right? It's always in a unique direction.
Yeah, except for one time, most of the time.
So let's say, well, if not equal is taken, right?
Mm-hmm.
So most of the time you are going to see ones here, and most of the time you are also going to see ones here.
Mm-hmm.
And if you predict 1, 1, if I see like 1, 1, 1, 1, right? So that's probably the most commonly used pattern, right?
Mm-hmm.
And if I predict 1, 1, 1, 1 as correct, as taken, right? You are only going to get it wrong for what? For 10% of the time.
10% of the time, yeah.
Isn't that the same as a local predictor?
So that means the global predictor doesn't do better there. That's what my group said. Right? Is that the conclusion
it's
you
not
want to
better,
say?
right? But the local is also not better, right? So they are about the same.
Mm-hmm. That's what we meant.
Okay, how about the second case?
The second case, because it's only one branch and it's most of the time it will be taken, I guess it will be about the same also.
Okay, how about the third one?
The third one, it seems like the global predictor would be better.
Why?
I think we arrived at that conclusion because there's more branches and it fluctuates. And I guess the X branch, I don't know if that fluctuates or not.
Yeah, well, but if you look at this one, right? This is essentially like if J equal to 0 or J equal to 1, right? Because your J can only fluctuate between 0 and 1. Right? So it's essentially like the X branch that we have in a previous case, right? So if you consider that, and it tells you that the global predictor is doing a better job.
Yeah.
Because it's an equivalent case as the previous slide, right? But how about the last one?
The last one, I think if it's a random number, there's a 50-50 chance that we'll take the X branch or not. So the I guess it's about the same. I'm not sure because the global predictor, it's random, so I don't know.
Right. So the thing is that, right? So that's why that's actually an example of the benefit of a local predictor, right? Because this part is random, right? And you are based on the history of this also, right? So this one will mess up your prediction because sometimes you see this, it says yes. Sometimes you see that, it says no, right? So it makes the global predictor really bad, right? And the local predictor is also doing bad on this one. However, even though the local predictor did a bad job on this one, but doesn't affect the fact that the local predictor can do a still good job on this one because both states are trained separately.
Yeah, because it's local.
Right? So actually only one case here shows the global history predictor is a better one. So that's why in modern processor, and thanks Dui, and in modern processor is actually a combination of two, and we will have we will dynamically select predictors among them. Okay, Harry's question.
So on behalf of my group, I have to say this. We had a massive problem with not truly understanding the difference between the global predictor and the local one, because from our perspective, like if each branch still has its own state, like we understand how the global register changes.
Predictor, each branch doesn't have its own state.
Okay.
Right? So if you go back and look at the graph that I draw here, right? The state is not in your branch target buffer. The state is indexed by your global history. Did you see that?
Right, and so here, because it's in the index is 4, is it implying that 4 should be taken?
Right.
Okay.
So it's decoupled from the PC.
Right, and so you can get situations where it will tell you a branch that has already passed. You know, it'll give you information about a branch that's already passed, or perhaps you get situations where it's incorrect in of itself. Okay.
Yeah. Yep. All right. So hopefully that will clarify that. And okay, and thanks a lot. So so this is one of the major predictor that we are used right now in processors. So definitely we want you guys to take a deep look of how this one will work. And so please go through my slides carefully because I don't think this part is in the textbook. All right, so right now, as I mentioned, an important focus of this class is that we want to give you a hardware concept to help you become a performance programmer instead of just a programmer who write programs, implement features. So we are going to introduce some techniques that would help you being a performance programmer on the era of modern pipeline processor. But before we start, I think some of you still remember, I don't know if that shocks you, about the demo we had in the very beginning of the lecture. We said if the option is 1, the complexity is higher, the number of instruction count is higher, but the end-to-end latency of the whole program becomes shorter. So how come does that happen? So given the knowledge that you have right now, I believe it's enough for you to answer this question. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so right now I would like to invite you to go to a group discussion, and I already sent out the questions through the chat. So before you enter the chat room, just click that file to see the question. So right now, let's start. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so after the discussion, the most popular answer is changed. So I just want you guys to tell me like what might change your mind and why you select your current answer or why you are sticky with your current answer. So can I have some of you sharing your thoughts? Okay, so I have Harris.
So our group answered B, and the one we thought was the correct rationale was number 3. The amount
Number
of
3.
Yeah.
Is it because we are talking about branch prediction?
Well, I mean, that definitely helps, but I mean, it's also a process of elimination as well as the fact that.
Okay, so why don't you talk about that?
All right, well, from 1 to 4, the amount of dynamic instructions are a lot smaller. Well, that's not necessarily true, because if you're sorting, you're going to dramatically increase the number of
so it's actually increasing, right?
Right. The amount of branch execution to execute is smaller. No, they're going to be about the same, assuming
actually more, because you also need branches in sorting.
Oh, I didn't know that. But if that's the case, then yeah, it's going to be more.
Right. Well, I mean, if quick sort, right, you have to compare and swap.
Right. Yeah.
So that's branch, right? Okay.
Amount of data accesses is smaller. Well, no, because sorting is going to require data accessing.
Right. So all of this, right, are giving us an intuition that with sorting it should be bad. right? So the only thing that makes possible is just this one, right? The amount of branch misprediction is smaller, right? So let's say this is like a branch X, right? So can you tell me, without sorting, can you like guess what the accuracy of branch X if you're well, like if your I, okay, say let's say like, can you imagine what's the accuracy of no sorting?
Of no sorting.
Yeah.
And what type of branch prediction are we using?
No matter what.
No matter what, huh?
Yeah. If it's random.
I don't think it's going to be very high. I guess it would be my prediction would be something like 50-50, but it would depend on threshold.
Yeah, 50, yeah. Right? 50-50, right? But with sorting, what would happen is that if in the very beginning, right, all my values are smaller than threshold, right? So in the very beginning, like when I start with 0 to some other place, right? Say like a value of j, right? Or say like everything within data I would be smaller than threshold, right? So you just guess one direction and everyone is going to be one direction, right?
Right.
So with sorting, the branch prediction will be 100% before the threshold. How about after the threshold?
After the threshold, wouldn't it still be 100%?
It still be 100%, right? The only thing that you will mispredict is when the transition occurs, right? But after the transition, after we retrain our predictor, no matter it's what's the name of it? No matter it's a bimodal or no matter it's a global history predictor, it's still 100%, right? So this tells you one thing. The sample code that I ran in the first lecture, the performance difference are completely from the mispredicted branch, right? So isn't that powerful? So the thing is, you thought branch is just one thing in the processor, right? But in modern processor, because the pipeline is so deep, we will talk about that later, but in modern processor, because their pipeline is so deep, so the stalls you have to suffer if you cannot resolve branch is a lot. If your branch prediction is not correct, it's going to be a lot, as you have to wait for many cycles, you have to flush many instructions as well. And needless to say, there are a lot of side effects that we will talk about later if we have time. But the thing is that if you see the performance difference between the sorting or not sorting one is completely from the fact that the branch prediction, and the sorting is simply making the branch outcome more predictable in a way that we can improve the application performance. So sorting, it seems like an overhead. However, this redundant overhead can be the factor that accelerating of the rest of the execution. Not sure how many of you were having the experience of dealing with database system. But in database system, when you store data, they always try to sort according to the most frequently used column for in a query. So the reason is because if you sort the data, the branch is going to be easier to be predicted. So your performance will be a lot better. So sorting is very important in performance optimization in many of the cases. So one thing that I want to tell you, if possible, to sort your data, if sorting your data won't affect the correctness of the result, go ahead and do it. And if you want me to tell you one of the most important algorithms you should know in CS100 or 101, that's definitely sorting. All right. So for this demo, the reason why with sorting is faster is just because branch mispredictions is smaller. However, other factors, adding the sort is indeed moving the program toward the direction that your performance would be worse. However, simply compensated from the fact that the misprediction is eliminated, that would result in the significant performance difference that you saw in the first lecture. All right, so now I'm going to have another demo. So this demo is called Popcount. So this is a question, or say that this is a very old interview question in many companies. And the reason why this question is important, so unlike a lot of leak code questions, they don't make sense at all because nobody is going to use that to solve a real question in their companies. But Popcount is indeed an important one, because if you work for companies that does storage, data center storage, for example, Facebook, Dropbox, whoever has data, right, like Amazon, right? Everyone needs that, the Popcount, to count the parity bits in error correction, error detecting, right? Every company likes to crypto their data, like to encrypt their data, right? And believe it or not, like Zoom said that they encrypt our data, although I don't believe that, but at least like crypto is everywhere, right? And another thing, like sparse matrix calculation, that also needs Popcount. And a lot of other data structure also use big vectors, Webley trees for that relies on Popcount. So this is a very important application. And the basic idea of Popcount is that simply count how many ones within a given number. So if I give you, so now the question is that I give you a 64-bit integer number. Find the number. Well, you guys like leak code, right? So I just reformat the question to be a leak code style, right? So given a 64-bit integer number, find a number of ones in its binary representation. Example 1, give you this number 9487, and the output is 7 because the representation is like this, and there are 7 ones within the number, right? So the question is that how to implement the Popcount, right? So actually there are, because this is not an algorithm class, so I already give you 4 different implementations, and believe it or not, they all works to solve the Popcount question. But the most important thing I wanted to think through is that which one is the best performing one. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to your voting result, looks like, well, quite a lot of you think A is the most efficient. Why don't you go ahead and discuss in group? I already sent out the question. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so right now I'm sharing with you guys what you guys think. Right, so according to what you have, A is still the most popular answer, and second by D, and E, nobody picks that. So right now I'm going to run all of them, right? So let's say I have this Popcount program, and so for if they find C, so if they find C, then I would run this function, which is exactly the C. And if I define B, it will run the B. And if it's D, it's going to be the D code. And if it's default, that's going to be A. So right now, let's compile it. And all of them, as you see, they are optimized. So some of you might complain about it's not optimized. So everything is optimized here. So let's run A first. So for program A, it's the very, very basic implementation that uses a while. And each time we just shift 1 bit. So this implementation also uses the bitwise operator, which people believe it would reduce the amount of computational overhead. But it turns out that we have been starting this for a while, and it takes about 30 seconds to execute. And right now, let's run a different version called B. So for B, it it unrolls the loop 4 in a run and check if the remaining value is still not 0, right? Because if it's 0, then we are done, right? So that's the implementation. But as you can see, this one still takes quite a while, but at least about 5 seconds faster than A. So definitely A is not going to be the answer. But how about C, which is an implementation? As you can see, it has a lookup table, which a lot of you might not choosing it because you think you think it's going to be more like data access overhead. However, even with a lot of memory instructions, this one's still 10 seconds faster than B, right? But look at D, right? Which is the one that runs the most of the loop, but looks like, okay, it only takes about 6 seconds. So definitely, as a lot of you, so a lot of you think about A, immediately you are probably thinking about like, okay, how come, right? So right now, the next question that I would like to ask you is actually this. So yeah, I saw some of you look at that. What, right? So right now, the next question I want to ask you is that why B is outperforming A? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so looks like most of you have an answer of it, but so can I just have like some of you like sharing what you think without going to the group discussion? So I have David. What do you think?
I think the answer is B. There should only be one of them that's correct.
Okay, what's the one?
I think that's statement 3.
You think it's statement 3 has
Yeah.
fewer branch instruction. Harris, what about you?
I think the answer is C. And the statements I think are correct are 3 and 1. And
3 and 1. How come B? So okay, so let's look at that, right? So so thanks a lot for your comments, right? So if you look at the code that we have here, right? We look at the code that we have here on the left-hand side, or on the version A and version B, right? Version B is actually using a technique called, well, so because of the time, I'm not going to introduce that in detail, but previously, do you remember that we have a question like this? Like we have pieces of a code like that, and you guys try that. You can never optimize the code, right? Because there's no way you can reorder it. However, there's a technique called loop unrolling. If I know for sure that the loop is going to be run for several times, if I expand the code twice, right? Like here, I start with load, add, store, add immediate, and branch not equal, then you will then figure out that I can combine the loop and eliminate one of the branch in the middle. And also for this add a plus 4, I can use the offset field in load store instruction to replace that add instruction so that I can eliminate 2 of the instructions, right? So in this way, you know, by unrolling the loop, it looks like more lines of the code from the programmer's perspective. But that's just what you see. What you see is actually not what you get, because on the compiler side, just because you write that redundant lines of the code that software programmers tell you, software engineering professor tells you is ugly, this kind of ugly code actually make your compiler easier to optimize. First of all, you can eliminate 2 instructions. So first, what Harry said, instruction count statement, that is true because you are having fewer instructions in the very beginning, right? And the other thing is that if you look at the code carefully, you will figure out you can actually reorder some of the instruction here, like instruction 3 and 4. If you make the 4 earlier, then you can avoid a stall. So what would really happen is that if you can unroll the loop, you can actually let the compiler reordering your instruction sequence like this without affecting the performance. And if you can reorder your code like this, and it turns out that this piece of the code will have no stall. It will have no stalls, right? So that's the power of unrolling. So here I just show you assembly level difference of these 2 pieces of a code. So for version V, if you unroll the loop, it looks like this, and it only have 1 branch per 4 iterations, comparing with A. So the number of instructions is a lot fewer, and here is giving you a rough idea about like how few it is about like I would say about like 25% smaller. And the other thing is that because you can rearrange your code like on the right hand side, like you can rearrange your code like this. So actually you could eliminate all data dependencies in the code to make your performance better. So if you look at the result, the first is correct, the third is correct, but also the fourth is correct because by rearranging your instructions after the unrolled loop, there are fewer data hazards. Harris.
So under what conditions can you unroll a loop?
So under what condition can you unroll a loop? Only when you know for sure unroll a loop won't affect the correctness. Only when you know for sure, for sure, for sure. Does that answer your question?
Well, I mean, the next question would be, well, when do you know for sure?
Right. Okay. Okay. Thank you. All right. So I think Harry is knowing me very well, right? But so then let's talk about why C is better than B. So I still want you to think through this question for 1.5 minutes so that I have some context to discuss with you. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, according to what you guys learned, wow, normal distribution. So can I have some of you sharing your thoughts? Because of the time limitation, we are not able to get into discussion today, a group discussion today. So if some of you would like to share your thoughts, that would definitely help us. Okay, so I have Tui, I have Harris. Okay, why don't I just make you guys a group and discuss right now?
You want to go first, Harris?
Sure. I thought the answer was B, and the one that the reason I chose was number 1.
Okay, I think number 1's also correct. But I'm iffy on number 2.
So look at number 2, right? Why do you think like that? For the pop count C and B, every time when you do while X, is the X different one from another?
For B and C?
Yeah.
No. Every time you do while X, I think the same X, because on B, you shift it 4 times in total.
For the branch misprediction or branch instructions, are they different?
I guess, yeah, no, there's no differences in branching.
Right. So in terms of data hazard, what do you guys think?
I mean, didn't we mention that once you unroll the loop in B, there's no stalling?
Right. So you are right. So actually, okay. So thanks for your discussion, right? So it looks like both of you reach a consensus that there's only one here is correct. And for the fourth one, well, because this one, as I said, is unrolled, so there's no data hazard, right? But for this one, there's an obvious data hazard depending on the load, because we need to look up the table, right? And the table is in the memory. So actually it has fewer data hazard, but it got the advantage that because each iteration, we only have this 2 major operators to perform. So it has significantly lower instruction count, right? But for others, it's all about the same, and probably C has more data hazard without architectural support. So the only one that makes C faster than B is just because the instruction count, right? So see, we are putting everything together, right? So now it's instruction count. But the biggest bazaar a lot of you might have is about D and C. So I really want you to think through D and C and just let me know why a lot of you think it's D later on. All right, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, so according to what I learned from you, It's almost like a tie, B and C. So can I have, well, because of the time limitation, I would like to do a co-classroom discussion like what Twee and Harris just did. Can I have some of you raise your hand, join the discussion? I think it's very good. Raise your hand. Okay, I have Harris again. I have Twee again. Okay, who else? Who else? One more. Just give me one more. Okay, if not, okay. Harris versus Twee, round 2. Okay, I also have Debbie. Okay, finally.
Yay.
Okay. Okay.
Yay.
Guys, go ahead.
Okay, I guess I'll start. So I picked B, and the one I thought was correct was reason number 2.
Wait, I'm sorry. How many you think are correct? I can't
1.
hear well. Okay.
Yeah.
I think also 1 is correct, but I think number 4 is correct only because in D, the loop is comparing I, not comparing X. So you don't have to wait for X to be done shifting and then take the branch. Yeah, and then like because X is 64-bit, if you keep shifting that same number by 4, the total time, I mean for C, I'm not sure if it'll be 16 times every time for the while loop. For D, for sure, it's 16 times every time, but because I'm not sure, I can't say 1, 2, or 3 is correct, but I know 4 is correct because of what I said before. So that's why I picked 1.
Yeah, wait, I agree with everything there. But one thing that I was like curious about was like, so like what is the value of X is like, because we know for sure that like 16, you know, it's bounded in D, but X could be anything. So that's why I was not sure, but I feel like D like is more likely to have a lower dynamic instruction count.
Okay, so
Yeah.
those are good discussions, right? And well, Debbie, you mentioned one thing that's really good about the loop. I will keep you guys all unmuted at this point because maybe you will, if you have any like idea, just jump in. So I'm like right now discussing with you, right? So first of all, like Debbie, you just mentioned one thing. You're not sure about X, right? Nobody is sure about X. So it means that this branch itself is hard to predict sometimes, right? So there are going to be branch mispredictions here, right? But how about the branch here? Is it easy to predict or hard to predict?
Easy.
Yeah.
Easy to predict, right? So who would have lower mispredictions?
D.
D would have. How about the branch instructions?
I would actually think it would be the same, the number of branch instructions on both.
Okay, so the bazaar here is about the instructions, right? So another thing that you might think about is that when I compile the code, I'm using compiler optimization. And to perform loop unrolling, not only the programmer can do it, compiler can do it. So some of you would like to say, I like to make this thing like an X, right? Some unknown number. And you think that would reduce the instruction count, but in fact is that will make your program slower because if you make this a constant number, then the compiler knows that, okay, you know you are going to run this iteration for 16 times for sure. So what actually, this is the translated code in your compiler. Your compiler would expand the loop internally without letting you see. So this is the actual code that compiler generated. So in this way, is there any branches still?
Not at all.
No.
Not at all. So definitely, right, D would have significantly lower misprediction because there's just no branch. There's no branch instructions at all. And because we eliminate all the dynamic the branches. So, and usually the X is a very random number and it's hard to predict, right? And in many cases, if it's a random number, it's evenly distributed. So dynamic instructions would not be in favor of C either, right, in this case. And the other thing is that, well, both of them have this data hazard here, but as we learned, because you unroll the loop, you can move all the load in the very beginning of the code and turns out that you can eliminate most of the data hazard by rearranging your code, right? So the answer to this one is that everything here explains why D is better than C, even though it's counterintuitive that you seems like you make more iterations, but actually this is because your code make the compiler easier to understand your purpose of the code. So it works better. All right. So thanks a lot. And I think all of you have a very, very great discussion. And so one big takeaway here is that for code optimization, you are writing the code that is making your compiler easy to understand, not writing the code that make yourself not just making yourself easy to understand. So before you leave the classroom, there are several things that I want to let you know. First of all, we have assignment 3 due tomorrow evening. It's all about branch prediction. We have midterm on Thursday. Make sure that you can attend the lecture on time. Well, actually 5 minutes before the midterm begins, because we want to check out your surroundings are good enough for us to convince that you are not cheating. And the lecture on Wednesday will provide a review, highlight, and sample midterms. And if you are worried about the lab, I just want to tell you, you can still interview during any time before the last deadline. Other than that, enjoy the rest of your day. I will see you tomorrow.